My name is Bill Thomas, Associate Vice President at Hampton University. We welcome the opportunity to present this year at the National Cancer Institute Quantitative Imaging Network virtual annual meeting. Our Hampton University Proton Therapy Institute is an associate member of QIN. First, a little background with regard to the history of our institution, which opened in 1868 by General Samuel Chapman Armstrong over 150 years ago on the same American shoreline that stolen African slaves arrived in 1619 in Hampton, Virginia. This week, we also celebrate the birth of Martin Luther King, Jr., whose mother, Alberta James King, graduated from Hampton University. Dr. King constantly reminded us of all the forms of inequality, injustice in health is the most shocking and the most inhumane. 10 years ago, Dr. William R. Harvey, one of America's longest-serving university presidents and visionary with over 43 years of experience, made a huge investment. Most importantly, he made an impossible and bold dream come true when he opened up Hampton's $225 million cancer treatment and research facility. Dr. Harvey made this investment with little support from either our state or federal government, but he clearly understood the cause, which was to make Hampton University a prestigious HBCU and a model research institution of higher learning that could take action and achieve results that would accelerate progress toward ending cancer as we now know it. For the past several years, Hampton has also worked with the Commonwealth of Virginia and the National Institute of Health project on the pathway to sustainability for historically Black colleges and universities with Diane Frazier and Annette Scarborough, and with the President's White House office on the initiatives for HBCUs. Our purpose was to gain programmatic support of the clinical translational research efforts at Hampton that were important for our mission. However, after meeting George Redmond from NCI's Quantitative Imaging Network during an NIH HBCU seminar, his guidance was remarkable. He quickly was able to help us understand our strengths, weaknesses, and potential. As such, we focused the science of extracting measurable information on a patient's conditions from clinical images by building up our infrastructure such as information was invaluable. For example, for more accurate cancer diagnosis. Robert Nordstrom and George Redmond provided leadership for Hampton to become an associate member of QIN, where we have been able to leverage support from the Virginia General Assembly, industry, and other leading research institutions around the world. By recognizing and leveraging our research, which currently includes 8 clinical research trials, research and radiobiological aspects of proton therapy, and other hadron radiation, including activated atomic medicine based on nuclear agents, research and development of methods and technologies for gated therapy delivery, and quantitative imaging research. We understand the importance of developing solid academic and industry partnerships. Our growing Hampton Cancer Research Team is working with other associate QIN members like Case Western University, where we recognize our different strengths, but work together in leveraging our common goals. Hampton University has a unique capability with its proton beam facility, not shared by most of the Quantitative Imaging Network members. For this reason, Hampton University Proton Therapy Institute membership in QIN and collaboration with its members is so important. The new collaboration research initiative championed by Hampton University promises new avenues for improved quality of care for all cancer patients and offer unique opportunities of addressing cancer treatment disparity issues. Any objective analysis of this vast amount of data requires smart, self-learning AI, artificial intelligence, algorithms. Development and use of AI in predictive medicine is a fast-growing field of research, promising improvement in the quality of care and the delivery of personalized medicine for all Americans. Our team looks forward to expanding our involvement in the QIN, and to a very successful meeting.
Hello, my name is Alejandro Carabe. I'm the new Chief Medical Physicist at the Hampton University Proton Therapy Institute, and I'm going to describe some of our research interests focused on the radiobiological optimization of proton therapy through artificial intelligence. A lot of this work was initiated while I was working at the University of Pennsylvania, and also was done in collaboration with other institutions such as Varian, which was the funding source for a lot of the work that is presented here. So some of the group research interests are the modeling of enhanced radiobiological effects in proton beams compared to photon conventional beams. And as you can see here in the image, on the upper image, we have a proton beamlet traversing coming from the left side of the water cube. And if we were to place different cell cultures along the beam axis, we would find that the cells would present different survival levels, mainly due to two reasons. The first reason is because at different positions along the beam, we have different doses, but also because the dose at the very distal edge, the dose quality, if you like, at the very distal edge is harder, meaning that you're going to see a deepening of the survival fraction of the cells presented to the beam. And this element in here is an element that is extremely interesting in order to take advantage from it when you want to optimize the effectiveness of your proton beams when used for radiotherapy purposes. So if we had a prostate case with a bilateral beam arrangement, where you have both beams covering the target, being the target, this contour area in the middle of the image, fully cover and homogeneously cover with dose, you will see that you're able with protons to cover the area, the central area, the target with a uniform dose distribution. And the advantage of using protons is that while you have an entrance dose, you don't have an exit dose to be concerned about. So you're able to protect some of the targets, some of the critical organs rather, placed at the distal edge of your beam. What it's important also to remember is because of that biological effectiveness at the very distal edge of the beam, one element that is currently not being considered in proton radiotherapy is the fact that that enhancement or reduction of survival of cells at the distal edge of the beam is not accounted for, and therefore some of the biological effectiveness is not completely, is ignored. So the group is interested in bringing that into the treatment planning process in order to fully account for those enhanced biological effectiveness. So the objective of the group is to bring those enhanced biological effectiveness areas of the proton beams into the target instead of being wasted outside of the target as shown in the image. So one of the things that we're planning to do is to study beam arrangements that are optimized through artificial intelligence. Actually, there is no artificial intelligence algorithm that factors in this enhanced biological effectiveness of proton beams at the distal edge of the beam. So the idea would be to extract that information from multiple plans and then use an algorithmic approach in order to provide what would be the best distribution of beams range around the patient that allow us to enhance the effectiveness right in the target instead of wasting it outside of the target. Of course, based on that principle, the following interest of the group is to create new delivery modalities that can take advantage of this modeling of enhanced effectiveness. And that's where the concept of proton arc therapy comes into place. You have to think that in radiotherapy, the majority of the techniques developed initially in the early ages of radiotherapy have evolved into rotational treatments That is still not the case in proton radiotherapy, but is currently one of the main interests that the field is focused on. And whenever you introduce arcing techniques, a lot of the interest is how can you make a more robust analysis, or how can you obtain a more robust amount of information on what is the best arrangement of the arc in order to produce the best effectiveness of your treatment and take advantage of your treatment for your patient. So this is an example of what you normally see when we run our optimization in proton arc mode. You have a number of features in here you can enable and disable, but we are in a position now where we can actually extract a lot of information from this tool and then plug it into an algorithm, an artificial intelligence algorithm, in order to extract the information that is needed for plans to be optimized at a later stage. This is a typical example of what happens with a patient that is treated with proton modulated arc therapy, as a difference to the standard pencil beam scanning mode. In here you have two beams coming to treat the target, as a difference to have a 360 degrees treatment modality that allows you to avoid doses to critical structure. And here you see the brain stem laterally being hit, or distally coming from this side being hit by both beams, whereas in here you have a much better, a much higher ability to overcome, to try not to deposit dose in that structure. One of the advantages that we are able to calculate is that based on some of our current algorithmic approaches, we're able to determine the difference in effectiveness due to both modalities in the target as well as the organs at risk surrounding the target. And you can see how proton arc therapy is able to avoid higher effectiveness, higher cell kills in the normal structures surrounding the target, and focus that higher cell kill effect in the target itself. And there's multiple cases in which you will see the exact same situation, regardless the complexity of the treatment. We now have also a new 3 Tesla MRI system at HUPTI, and the advantage of having this system is that we can get metabolic information from our patients once they are before treatment and after treatment. So then we can also obtain that information and plug it into artificial intelligence algorithm in order to obtain a much more robust approach about our planning process. And of course, the objective is to maximize the tumor control and effectiveness while minimize the radiation toxicities to the normal tissues. Thank you.
Hello, everyone. My name is Anant Marabushi, and it gives me great pleasure to talk about this new partnership between Case Western Reserve University and Hampton University around radiomics and quantitative imaging for targeting prostate cancer and health disparities. Our group at Case Western, the Computational Imaging and Personalized Diagnostics group, also happens to be a quantitative imaging member associate status. So just very briefly about us and our group. The Center for Computational Imaging and Personalized Diagnostics at Case Western Reserve University was established back in 2012. It has now grown to about 60 people, been generously funded through grants through the NIH, primarily through the National Cancer Institute. And we're tackling a number of different projects broadly under the umbrella of artificial intelligence that spans multiple different length scales, everything from imaging to radiology to pathology, genomics, as well as electrophysiological data. Just to give you a little bit of a glimpse of the scientists, students, postdocs, and faculty colleagues at the Center for Computational Imaging and Personalized Diagnostics at Case Western. And so in the last few months, we have embarked on a partnership with Hampton University. Hampton University, of course, is an HBCU that's located within Virginia, which within its catchment area covers a number of military personnel as well as veterans, and also, unfortunately, happens to be in a catchment area that sees a very large cancer incidence, particularly in the area of prostate cancer. And so one of the particular questions that we in our group have been trying to address has been the role of artificial intelligence to address the issue of overdiagnosis and overtreatment of cancers. And there is a wide recognition now that overdiagnosis and overtreatment causes real harm to patients. Prostate cancer is a classic example where 1 in 6, 1 in 7 men will be diagnosed with prostate cancer in his lifetime in the US, but only 1 in 40 will actually die on account of it. And while a lot of these cancers typically tend to be more indolent, they tend to be treated in a fairly radical manner, either through prostatectomy or through radiation therapy. But apart from the patient-centric effects of this radical therapy, that is the morbidity associated with these radical therapies, we have to acknowledge that at least in the US, there is a very real issue of financial toxicity. Some startling statistics like the ones that you see here, where more than 42% of new cancer patients can lose their life savings. And a large part of this has to do with the issue of overtreatment and overdiagnosis of cancer. And so as part of this partnership between Case Western Reserve University and Hampton University, we're going to be working together on artificial intelligence for cancer imaging, looking at the role of AI for detection and diagnosis of prostate cancer, looking at AI for treatment plans and predicting cancer outcome, as well as looking at the role of AI for cancer disparities, looking to try to create population-specific diagnostic and prognostic models. One of the things that our group has been working on for the last 15 years and actually currently funded through an NCI R01 is the role of AI and radiomics for prostate cancer detection from MRI scans. The ability to identify with AI and radiomics on routine MRI scans the presence of cancer could actually help identify those patients who truly need a biopsy, because we know that a lot of men with elevated prostate-specific antigen levels, there really is no cancer. It's a false positive. And so we're looking as a part of this NCI R01 that we then want to extend and collaborate with Hampton U is to look at the role of AI to help address this issue of unnecessary biopsies. Another area that we're looking to collaborate on is the work that our group has been doing around artificial intelligence to target, in a very precise and specific manner, radiation dose plans for prostate cancer patients. Hampton University, of course, recently acquired a proton therapy treatment modality for radiation treatment of prostate cancers. And so we're looking to partner with Hampton University to use artificial intelligence to identify exactly where the focus of prostate cancer is, so we can start to create very specific dose plans that can then be used for targeted treatment with proton therapy. Another area that our group is focused on is in the role of pathomics, essentially the use of AI computer vision tools to computationally interrogate digital pathology specimens to try to prize out subvisual imaging features and imaging biomarkers that describe the morphology of the disease in a highly quantitative manner, while all the while doing this in a non-destructive, tissue non-destructive digital manner. One of the application areas for this kind of pathomics technologies is in predicting the risk of recurrence in prostate cancer men or prostate cancer patients after surgery. And our group has shown that by extracting features relating to gland shape, gland morphology from prostate cancer surgical specimens, we can actually predict which of these men are likely to have a recurrence of prostate cancer after surgery, and therefore which men would greatly benefit from treatments like adjuvant docetaxel or adjuvant radiation therapy after radical therapy. In fact, one of the things that our group has also demonstrated is that this kind of tissue non-destructive technology is just as accurate in predicting risk of recurrence after surgery compared to very expensive molecular diagnostic tests, one of which is the Decipher test, which is a 22 gene expression based assay. And so in a head-to-head comparison, our group has shown that our digital pathomics approach is actually non-inferior to the Decipher test. The Decipher test is a $3,000 test, and our test actually could potentially be orders of magnitude lower in cost, because we're just talking about image analysis of a digital slide of a prostate cancer tissue specimen. What is also great is that the combination of our image pathomics-based test with very standard clinical variables like prostate-specific antigen as well as Gleason grade actually turns out to be even superior compared to the Decipher test. And this is really, really exciting and another venue for collaboration with our partners at Hampton U. And finally, another area that we're very, very excited on, in particular in partnering with Hampton U, is the work that our group has been doing around the role of AI and pathomic approaches to look to understand differences in prostate cancer appearance between Black men and white men with prostate cancer. In work that we recently published in Clinical Cancer Research, our group showed that using AI, we could tease out subtle morphologic differences in the appearance of prostate cancer between Black men and white men with prostate cancer. Why is that important? Well, we then were able to demonstrate in this work that creating population-specific models with these features identified from prostate cancer of Black men was better able to prognosticate the risk of recurrence following surgery compared to a model that didn't account for population-specific differences. In other words, when you actually use the signature learned from Black men with prostate cancer, that signature was very prognostic when applied to a new set of African-American men with prostate cancer in predicting their risk of recurrence versus a model that didn't explicitly account for these differences. That is, a population-agnostic model was not as effective or accurate as one that really accounted for these population-based differences. So this, again, is an area that we're really looking to work with Hampton University on. And finally, just want to again acknowledge the fantastic students, postdocs, staff, and faculty colleagues at Case Western Reserve University that are helping to move the needle forward on artificial intelligence for precision medicine. And again, just want to thank generous funding from the Department of Defense, but also critically and mostly from the National Cancer Institute in supporting our efforts. Thank you very much.